Number 19 says the value of delta G for a gas phase reaction right here is negative 100 kilojoules per mole at 285. Calculate G, notice that's G at non-standard conditions for the following non-standard conditions. See, there's no little circle up there. So the equation we're going to use here in number 19 and 19.5 is that G at non-standard conditions is equal to G circle plus RT natural log of Q. And so filling in the numbers here, G is equal to the standard conditions G, which is negative 100 kilojoules, plus R, and remember R's got to be in kilojoules, so be careful of that, 0.00831, and that's in kilojoules per mole, times Kelvin, kilojoules per mole Kelvin, times the Kelvin temperature, which is 285, times the natural log of Q, and Q of course is products divided by reactants to the power of its coefficients, and so you see the product here is NH3, so that's ammonia, so that would be 5 and to the second power, divided by the reactants nitrogen, which is 0.01 raised to the first power, times hydrogen, which should be raised to the third power, 3 to the third power. So you want to evaluate this part first right here and then take the natural log of that. And so if you do this on your calculator right here, you end up with 92.6. You want to take the natural log of that, of course. And then once you take the natural log of that number, you end up with 4.52. And then you want to multiply those times this right here. So when you take 0.00831 times 285 times 4.52, you end up with 10.72. Now you want to add that to the negative 100 right here, knowing that this is in kilojoules and this is in kilojoules. And so your delta G ends up being a little under 90. I believe it ends up being negative 89.3 or so. And the units on that would be kilojoules. So that's a non-standard condition one. Now number 19.5 is very similar. This one, just to show you where the equation is, remember that here is G is equal to G circle plus RT natural log of Q at non-standard conditions. So G is equal to G circle plus RT natural log of Q. And it tells us that the G at standard conditions now is negative 100 kilojoules, plus R, which is 0.00831 kilojoules per mole times Kelvin, times the temperature, which it tells us in here is at 285, times the natural log of Q. And Q here would be 2 on the top. Don't forget to square it because there's a 2 in front of it. Divided by nitrogen, which is 2, times hydrogen, which is 1 to the third power. So take the natural log of this, and this is 4 divided by 2, so that would be 2. So the natural log of 2 is 0.693. Then you want to multiply that times 285 times 0.00831 plus negative 100 kilojoules. This area right here, when you multiply all those together, ends up being 1.64 plus negative 100 kilojoules, and so you end up with negative 98.36. That's to 4 sig figs, so negative 98 to 2 sig figs kilojoules. There's only 2 sig figs right here in that 2 atmospheres. That's 19.5. Now, in number 20 and 21, there's a phase change going on. when there's a phase change going on, you can calculate the entropy directly by knowing that the entropy is equal to the negative of the enthalpy divided by the Kelvin temperature. S equals negative H divided by T. This is for 20 and 21. So for number 20, it says the normal freezing point is, and you have to convert that to Kelvin right here, and the delta H is 25.5. Now it does want it in units of joules per Kelvin right here, so you have to watch out because this is in kilojoules. And so for number 20, delta S is equal to negative delta H divided by T, and that's going to equal negative 25.5 kilojoules divided by 298.5 Kelvin, converting this 24.7 right here to Kelvin. So 24.7 plus 273 equals 297.7. So let me change this just a little bit here. 297.7 Kelvin. Okay, and then dividing those two would be negative 25.5 divided by the answer, and I end up with negative 0.0856. And remember, that's in kilojoules per Kelvin, and we want it in joules per Kelvin, so 1, 2, 3 to the left would give us negative 85.6 joules per Kelvin. 21, delta S is calculated the same way, H divided by T, and in this case we have negative 75.5 kilojoules divided by the 273 plus 54.7 for this temperature right here. So 327.7 Kelvin. Let's do that division now. 75.5 divided by second answer, and I get a negative 0.2304. Remember, that's in kilojoules per Kelvin. So 1, 2, 3 over gives us negative 230 to 266 joules per Kelvin. Number 22, which property of the system must decrease in a spontaneous process? Well, G has to be below 0. So it has to decrease to be spontaneous, and so you have to see that delta G is the one that has to decrease to be spontaneous. And which process indicates an increase in entropy? So entropy will increase when you go from a solid to a gas, because obviously a gas has many more microstates that you can be in. From a liquid to a gas, because a gas is much more spread out. And then the other ones go from gas to gas, but we went from 1 mole of gas to 2 moles of gas, so it would also increase for that one. This one right here goes from gas to solid, that would decrease the entropy, and this would go from gas to solid, and that would also decrease the entropy. So those three would be entropy decreasers. And then the last question, which is our endothermic reactions? So look at the start, look at the end, does it go up? Look at the start, look at the end, does it go up? So both C and D go up, so those would be endothermics, so letter D. And then which possesses the largest activation energy? So here you have to be really careful and look at the scales on here because they're different for each one. So here we start at 100 and end at 300, so you would have 200 for activation energy there. Here it might look taller, but you're only going from 100 to 250, so you'd have 150. And so D right here would be the one with the largest activation energy.